come here and mention two things. Um, since there's only one person. Is that serious? Oh, that is good. Due date is the 20th, but what I should have is an end date, which is, say, the 23 at 5. Hopefully that means that you guys should still be able to submit, right? And was it you who couldn't submit because it was past midnight? Or somebody who sent me a frantic email. It's like, it's past midnight. At like 12:15 or something like that. Okay, so now you can submit, and we'll talk about it Wednesday. Remind me so we actually talk about it. Let me actually mention this. We have assignment 2. And we're going to spend kind of this week reviewing different data structures and things like that. And we're going to talk about order, right? Big O notation, right? So it's supposed to be n squared. I want you guys to deeply think about what the heck does that mean, right? And so what I'm asking you to do is to get something probably from Java, right? If you have something else, let me know, we can talk. But where you have the same interface implemented 2 different ways, right? For example, with an array or vector, right? You have the array list class and the linked list class. They both implement the list class. They both have get and set and those kinds of things. But they have very different implementations that should have very different running times, right? Or with a set or a map, you can have hash table implementation versus tree implementations, right? And those, as we'll see, are supposed to have different O notations for the operations. So what I want you to do is to get 2 of those things, right? And I'm actually listing linked list versus array implementation of list, or hash table versus tree-based implementations of sets or maps, and compare at least 2 of the operations. Get something like, okay, I'm going to check insert and search, or insert and delete, right? Do it, get times, and you can use either, did I put it here? No, I didn't, of course. How do we get time? In Java, there is system.currentTime millis and system.something else. How do we get time in Java? Meta answer. How do you find it? Google, right? Apple tab, Bing, Stack Overflow, Google, whatever. I work for Microsoft. Bing is now my default search. Java time. And Java time, milliseconds, Java current time. There is 2. There is current time millis, which is in milliseconds. And then there is a something like that, high resolution, which is, God, nanotime. One gives you, current time millis gives you, what do you think? Current time in milliseconds, and nanotime gives you? Nanoseconds, right? How many nanos to a milli? No, 1 more, million. Milli, then micro, then nano. So 1,000,000 nanoseconds are 1 millisecond, I think. Maybe. I think it's 1,000,000. 1,000,000 nanoseconds is 1 millisecond. So an American billion nanoseconds is 1 second. Different. In the US, a billion is 1,000 million. In half the other places, a billion is a million. No, my thing. In Spanish, it is a million, and they have come up with weird things. In India, what do you guys do? You use lakh for American billion, and
Lakh to millions.
lakh is 1 million, or
Lakh is 100,000.
lakh is 100,000. Okay.
1 crore is million.
Crore is million. Okay. And a billion is what? Who knows? It's a lot. Okay. In French and Spanish, billion means millions. I have no clue what it means in other places. So basically, start the timer, right? Insert n things into an array list. Check the time at the end, right? And I'm asking you to do that, use different n values, and kind of plot it for your two things. Does that make sense? And then what I really want you to do, and I'm assuming that this is going to be an iterative process, is to analyze the result and start thinking about that kind of stuff, right? First of all, if you run it again, do you get the same result? Chances are that you don't, right? It should be close. Should be close. Actually, once you get to ends where the running time dominates the stuff, it should be close, right? The first few, what happens when I check insert one element into an array? How long does that take?
No.
Constant, but what's that constant? Is that huge constant or tiny constant? Tiny, right? So chances are that actually calling get current time millis or nano time is much slower than inserting an element into an array, right? So for when n is 1, I'm just getting noise, right? No signal whatsoever. When I get to a certain size of n, that will depend on the data structure you choose, what kinds of things you're inserting, what computer you're running it on, right? Then you start actually getting closer and closer times. How big is the variance, do you think? If I run it, I insert 1,000,000 elements and I get 2 seconds. If I run it again, what am I going to get?
Probably a few milliseconds difference.
Is it a few milliseconds difference? Is it 3 seconds rather than 2? Is it, right? Have you done it? No. Then, I mean, it's a pretty good guess. That's probably what will happen, but, right? I want you guys to do it and run it several times, and right? And start thinking about that stuff, right? And see what the heck does it mean in practice.
I mean, unless you start running other software in the background, which affects the time. But.
Maybe, right? And can you derive the constants from the data, right? If I'm telling you, well, or the theory says this takes order of n squared, right? So that means Cn squared. What's that C? Can you derive it? Can you reasonably say, yeah, this is, right? Do the results go with theory? How much they deviate? And you're going to see that, what do you think happens? They're going to be very close to theory? Maybe. There is tons of other stuff happening on your computers. There is caching, there is garbage collection, there is oodles of other stuff going on with your computer that may change the result. So, the data matter. What happens when you put different, right? putting larger integers matters. Do putting strings rather than ints matters. What, right? And then kind of like, well, this is what I did. Here's which implementation I think is better. And you need to kind of say, well, better for what, or right? Better in this case, that kind of stuff. Does that idea make sense? You understand what's the assignment, you understand how to do it, yes?
Are we plotting it in, are we doing, calculating it in milliseconds, or we have to do it in nanoseconds? Because here's the thing, right?
Whatever you prefer.
Because if there is a small difference in milliseconds, that's okay. But at the same time, the difference will be exponential in nanoseconds.
Not exponential,
But
it'll
like,
just be
it'll-
larger.
it'll be-
Just be
yeah,
a constant factor larger.
So is that okay, or?
That's okay because it's going to be the same percentage,
Right,
right?
right.
Or actually, what you're going to see is that which one you use matters, but you're going to see that one of them makes sense and the other one doesn't,
Right.
right? Because it may be that the one in nanoseconds doesn't make any sense because I have too much variance, right? If I'm doing, it's just too much noise. But I don't know. It depends on what you choose. Depends on your end. Depends on your computer. Depends on all of that stuff. So I just want you guys to think. And I expect you to give me source code, right? And it doesn't have to be beautiful source code, right? It can be stuff where you change constants, right? And right, it can be messy source code. It doesn't have to be pretty. And a 2-page-ish paper with the plot and analysis. Right? I want you to show me these were my ends, these were the times, right? 2 different colors or something like that for 2 different things. For the 2 different data structures, right? And maybe 2 plots, one for insert, one for delete, or whatever you're doing. And then analysis. Here's what happened, here's where I had difficulties, these numbers don't make sense to me, all of that stuff. Does that make sense? What does 2 pages means? Means 4 pages. No. It means 2 pages is the goal, is not a mandate, right? Don't go changing font sizes to make it either. Hey, you all have done it, right? For 2 pages with 16 type font. And double spaced, right? Versus 2 pages with 10 type font and single spaced and ½ inch margins, right? It's just a goal. Don't torture it so it fits in 2 pages. Say what you need to say. If it's 3 pages, that's cool, right? If it's 1.5, that's cool. If it's 1 paragraph, that's probably too little. If it's 20 pages, that's probably too much, right? I mean, 2 pages is a target, is not a mandate. Don't force it to fit in 2 pages. Does that make sense? Some of you will be more verbose and will take 3 or 4. It's okay to take 3 or 4. It's not okay to take 30 or 40. Doesn't have to be a formal paper. You don't have to cite references, right? Expect it to be your work, right? You did the measurements and you start thinking about stuff. I want to see that you are thinking about it. That is the point of this assignment. Does that make sense? And you'll probably be surprised about what happens. I was doing this on the weekend. I do the assignments before I assign them to you. And this is the first time that I'm doing this class, so I'm just making them. And I will probably stop assigning stuff every week just because I know that I'm killing you and I'm killing myself with grading. My penance for assigning it is that I have to grade it and there is 40 of you and 1 of me. So. But we still need to figure out how to make the concepts fit and stick. Any questions? No? And I hope, let me make sure that I did the same thing. Yes. I have the 27th as the due date and the 30th at 5, which is next Wednesday. So it's due this Sunday at 11:59 p.m. Yes. with grace period until Wednesday before classes. Cool.
So the grace period, no penalties, right?
10% penalty,
Oh.
if I remember. I never remember. Here's the deal. I never remember. On the other hand, I don't want it, right? I don't want you to start thinking of, oh, the deadline is Wednesday, because then you're gonna miss the Wednesday real deadline, right? So I say 90%, sometimes I enforce it, I seldom enforce it just because when I'm grading it's a lot easier to just keep grading everybody and not worry about it. So my laziness works in your favor. Sorry, my optimizing the amount of work that I do work in your favor. But don't assume that that's the deadline. The deadline's Wednesday, because what will happen is we'll talk about the assignment on the class, and once we talk about it, then I'm not taking any assignments from anybody. Does that make sense? Cool. So let's quickly finish this stuff. That we were talking, and then we'll start talking more about this stuff. So we talked about algorithm analysis, right? We talked about this idea of running time based on n, right? Polynomial means it's okay, reasonably, right? When the input size doubles, the algorithm takes double the time, or some constant of 2, right? Maybe 4 times the time, or 8 times the time, but not 500 million times the time, or depending on n, or something like that. If an algorithm is polynomial time, the above scaling property holds. Basically, there are constants c greater than 0 and d greater than 0. For input size n, the running time of the algorithm is bounded by c n to the d, right? So there is a polynomial that bounds it, and then we talk about, actually this is important, right? Talked about worst case analysis. That's kind of what we worry more about, right? And then 3 slightly different versions of average, right? Probabilistic, if we randomize the algorithm, then the expectation is now probabilistic, right? It's truly average and doesn't depend on the input, it depends on the random numbers that we chose in the algorithm. Average case is expected over all inputs, and when you do average, you kind of assume that every input is equally probable. Whereas if you shuffle the things by yourself, you are not assuming that. You are making every input equally probable. Does that make sense? We'll see for some like sorting algorithms, if the input is sorted or complete reverse sorted, right, your algorithm will perform much worse or something like that. So rather than have those things, you can randomize and then don't depend on the input. And then amortize is mostly for data structures where you're going to be doing a sequence of operations, like you're going to have an array and you're going to insert 1,000,000 times. So that's a slightly different version of average. You're averaging over the n operations that you're going to do. We defined big O, right? T of n is O, big O of f of n if there are constants c greater than 0 and n0 greater than or equal to 0, such that T of n less than or equal than c times f of n for all n greater than or equal to n0. There's the alternate definition. We tend to use equal instead of is in. Omega is kind of the reverse-ish of this, right? In here we have less than or equal. In here we have greater than or equal. except that the fact that there exists and things like that don't make them necessarily, right, the converse of each other. And big theta is what we normally want, which is the tight bounds. So you are big O and big omega. You are, to abuse notation, greater than or equal and less than or equal, so you are equal-ish. Does that make sense? We talked about some of these kinds of things, and these are basically math and those definitions, right? Then we started talking about some of these things. We talked about linear times, right? Running time proportional to the input size, like max and min. Merge with extra memory is also linear time. Linear-arithmic time is n log n. They don't mention log n. Binary search is log n, right? A lot of the sorting algorithms are n log n. And then there's a bunch of problems that are solved by sort and then do a linear thing, right? And so ends up being sort dominates, which is n log n, assuming that you use an n log n sorting time. Quadratic, kind of the standard example is enumerate all pairs of elements. Sometimes you have other ways, right? And so in chapter 5, they promise a algorithm that will find the closest pair of points, the pair of points that's closest to each other in something that's better than order of n squared. Sometimes we can cheat in different ways, and we'll see that kind of stuff. Cubic time, enumerate all triples, right? Polynomial time, other kinds of polynomial time, right? Of course, linear, n squared, n cubed are polynomial.
I'm sorry for the wait.
It's okay. Find all subsets of size k of a given set is order of n to the k, right? And it doesn't matter, well, it matters differently how many elements you have than the k, right? Exponential, actually, finding all subsets of a set of size n, right, rather than all subsets of size k, is also exponential. An independent set, what's the maximum cardinality of an independent set? Is an order of n squared 2 to the n. So basically get all subsets of nodes and then check whether they form an independent set. Sublinear is anything less than linear, so log n and those kinds of things. Interesting thing about logs, they are less than any polynomial, right? Log n versus n, who is less for large n? Log n. Log n versus square root of n. Log n. Log n versus n to the 0.0000001. Log n, eventually. Does that make sense? It's less than any power, positive power, right? So, and n log n is also in between n and n squared by convention, but it's between n and n to the 1.5 too, if you want to. This idea makes sense? Cool. Now, let me abandon my training wheels and go find stuff. Hopefully it's there. This. Yes. We will eventually talk about algorithms. Probably the only notable algorithms you know, other than binary search and mix and max and min, are sorting algorithms, and we'll go over them just for fun. But we will be using a ton of data structures, and so I wanted to give a quick overview of them. Chances are that you have, I am hoping that you actually took a data structures class at some point in your life, maybe last semester, maybe 20 years ago when you were an undergrad, where you saw these things, right? And the idea of this class will make it so that this stuff becomes easy. But if you haven't done so, go implement one or two of them. If you haven't done so in a while, go implement one or two of them. It's always a fun thing to do. We have linear data structures that basically represent bunches of things, right, in one dimension. And so by implementation, we have two main different implementations. We have actually the array. What is an array? Sorry? Similar elements, right? But they are contiguously in memory, right? One after the other. So I get from the operating system, I get a chunk of memory and I stick 10 ints in there, right? If each int is 4 bytes, then I get 40 bytes, and they are one after the other, right? Arrays cannot, or the basic arrays cannot grow or shrink, right? I got 40 bytes, I got 40 bytes. So we have two ways of implementing linear data structures that grow, and I call them linked lists and vectors. Vector is actually named in C++, and that's where I learned it. Java has a data structure called a vector, which they don't like anymore, so now they prefer you use an array list. It's the same basic data structure, slightly different class. And array list is actually confusing because it's not a linked list, it's an array. But the interface in Java is called a list, which kind of makes sense, except that I hate it because you have linked lists, and those are lists, right? This thing is not a list. It's a, yeah. I hate it as a name. It's okay, but by their use, right, we sometimes use them as just a bunch of things, but we also use we can also use them as stacks. What's a stack?
First in, last out.
Yes, last in, first out.
Last in,
Same thing. Same thing. It's downside up, not upside down. And a queue is first in, first out, right? We'll see that actually stacks are super easy to implement with either one of those two. Queues are a lot more painful. And then a DQ is a double-ended queue, so it's something that you can make it work as a stack or a queue. And then we have priority queues, which are actually implemented very differently. A priority queue is one that is sorted-ish by priority. So if you're doing simulations or something like that, you'd have a queue usually sorted by when should this event happen or something like that. That's a priority queue. What? Ah, there it is. Cool. What's a linked list? What does it look like? Looks like something like this, right? When you go implement it. Java has generics, and I tend to use them when I can. They're actually a lot more painful to use even than C++'s templates, but oh, right? So this is how we define a generic linked list class. We define a class called linked list, and this is my type parameter, so it can contain ints or floats or whatever I want. inside I declare, or I could put it outside, a node for the linked list that contains a data element and then a reference in Java, a pointer in C or C++ to the next element in the list, right? And my list is really just a reference to the first node in the list. Does that idea make sense? You have done this a million times, right? Yes. Okay, 1,000. You went over this in data structures. You remember that stuff, right? You could do it with one hand tied to your back. Cool. Some variations. The kind of normal one, the one that you see more, is a single linked list. There is a double linked list, and I don't know what's correct English and what's standard usage, but I tend to call it a doubly linked list. That's you. It's a place where English kind of sucks. What is the idea? Instead of just containing a pointer to the next element, I also keep track of the previous element. Does that make sense? When I have a doubly linked list, many times I keep in my list not just a pointer to the first element, but a pointer to the last element too, right? And that allows me to insert at the end. And there is also the idea of a circular linked list where the first element is where I keep the pointer to the last element. And so I just have, as Alice says, have one pointer to the beginning, but I can go either way. And depending on how you build it like that or not. Does that make sense? There is a really cool data structure that's cool just for fun, called a skip list, which is like a linked list, but you keep pointers to elements in the middle, and in 3/4, something like that, so you can actually access a given element in logarithmic time. Does that make sense? So if I know the middle element and I need one that's above, I know the length of my list and the middle element, I can just go and do something like a binary search to get to the element number X. Does that make sense? How efficient are linked lists?
As long as you're inserting at the front.
Well, inserting at the front is very efficient, right? How much extra memory am I wasting? One pointer, right? One extra pointer per element. Does that make sense? They are efficient at inserting at the front and accessing the first element, right? How efficient are they to accessing the nth element?
Not very efficient, because you have to cycle through each one.
Yes. So what do we call that?
Linear.
Brute force.
Linear, right? We use linear time, right? Accessing an element is linear, which is horrible, right? How about inserting in the middle?
Yeah.
It's also linear because I need to find the middle, right? Does that make sense?
Yeah, but then you have to push each.
No, I don't. I
No,
just,
okay.
yeah, I don't need to move stuff in the middle. I just need to create a node and play with my pointers. But it's still linear because I need to go find the middle. Does that make sense? So insert at front is order of 1, get is order of n, or linear. Two things that make linked lists kind of suck in practice. One is every insertion, I need a call, I need an allocation of memory, right? And that's a constant time. It's just a relatively large constant time. I need to go call the operating system and tell it, hey, give me a piece of memory, right? So I can optimize and things, but it's relatively heavy, right? The other thing, what really makes them really suck, is locality of reference. We have this beautiful idea of RAM. What does RAM stand for? Random access memory. What does it mean?
Really fast memory.
It makes really fast, but what does it really mean? If it was really fast, it would be RFM. Sorry? I do not have to go through all the records. It takes me the same amount of time to access any location in memory, right? Does that idea make sense? That's what random access means. Is it true? No, it's a horrible lie. Why? I mean, it's, even when it's not true, it's still really fast memory, so in that sense it is okay. But it's a horrible lie. Why?
Some things might be cached.
Yes, caches. How does a cache work? You remember your computer architecture class. How does cache work?
Temporal locality.
Okay, what does that mean?
It
The most
predicts.
recently used.
Old version of something. You don't have to.
If you just use something in memory, you're more likely to use that again.
Or, right, that's
Or things
not the
near it.
computer architecture cache, right? Basic,
Or I want to think about geographic memory or spatial memory, where
yeah,
if I'm going to pull from this memory slot, I'm going to pull from the adjacent memory slots.
yes. So when I ask my processor to get memory 100, right, to get the byte 100, processor says, oh, I know you're going to want 101 and 102, right? I mean, that's what you're going to want. So you ask for 100, and the processor asks for 1 to 200 and puts them in the cache, right? So if you access 101 and 102, right, those accesses are super fast. If you, after accessing 100, you access 300, what happens?
It takes a little while.
Has to go get it from RAM, and that's very fast, but way, 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 way slower than cache.
So by the nature of RAM, when you allocate a new node to a linked list, it's not necessarily going to be incremental from the last memory allocated. It's just going to pick whatever is the easiest access in the RAM. You know, I'm sure there are special cases, but that's the idea of why it's not
Yeah.
efficient.
Yes,
Okay.
it is not necessarily contiguous. It's somewhere. Maybe contiguous, depending on what's going on, but it may not be. And that's your operating systems class. You get to study those algorithms and why would you choose one versus the other and things like that, right? But it just happens to, in general, not be contiguous, right? And so with this stuff, you have them all over, as opposed to an array where they are one after the other. And so if you can use an array, it's going to be so much faster, not just because you don't have to navigate, but also because if you iterate over them, they are one after the other. Does that idea make sense? So that's called locality of reference, right? Your references are next to each other. Your things are next to each other. And that makes performance better.
But there'd be a chance that if you call an array, that the cache is not going to necessarily pick up the entire array.
Yes, it will almost guarantee, unless your things match perfectly, right? It will not pick the entire array,
Right.
but it will pick the next 10 elements, right? So for those 10, you're super fast, and then you become slow for the next one. It's still a lot faster.
Yeah, understood.
It's not going to fit perfectly unless you're incredibly lucky. Does that idea make sense? On the other hand, linked lists are still widely used. Each allocation is tiny, right? So actually, operating systems use linked lists. The Linux kernel uses linked lists for half its internal data structures. I'm sure the other ones do too, but that's the only one where I actually have a clue about. No, not that I know the Linux kernel. But. As an aside, and this is something that I also expect you guys to know because we're going to be using all the time, recursion, right? Most linked list algorithms actually can be done without recursion. You probably did them with while loops and things like that. But many times, recursion makes things easier to explain. So if we wanted to get the size of a linked list, right? We would, or I would, sometimes, define a function like this. A recursive function, right, that takes a node and returns this size, right? The node, I'm calling it current head. If it is null, what is the size of that list? 0. So I just return 0. Otherwise, I return 1 plus the size of the next element in the list, right? And so eventually, this will give me the size of the list. Does that make sense? Do you all remember recursion? It's easy, not a big deal, right? Yes? Cool. Now, vectors. And we're probably going to go implement them because why not? What's the idea of a vector, right? It is like an array. In fact, what I have is an array, right? But if you ask me for a vector of 10 elements, I'm going to be sneaky and get an array of 20, right? And then if you ask me to add an element, I'll just add it at the end, right? I have 11, 12, life is good. What happens when you keep adding and you get to element 21?
Double it again.
I need to get a bigger array, right? Copy the elements, which is horrible, and then deallocate the previous array, right? And now I have this bigger array. Does that idea make sense? How big should the new array be?
I've always heard double.
Double. Why?
The larger you make the list, the less you have to allocate.
Why not triple? Why not 1.5?
Makes sense.
2 is a simple number. As long as we do, I think I'll need to check the math. As long as we keep doing exponential, right? It's gonna work because we just get different logarithms, right? What's gonna happen if I double, right, the array? How many allocations and copies did I do? Right? Here's the deal. If I come with an array of 1,000 elements that is completely full, or 1,024 elements, and I started with 1, how many times did I double that thing? 10 times, right? In total, how many times did I copy my elements and things like that? 10 times, but of different sizes. How many total elements did I copy?
10.4.
Yes, just about the same number. Does that make sense? Because I copied half and half of half and half of half, right? So the math works beautifully, so good. That's why we use 2. Because why not? Doesn't have to be 2. In fact, when you go play with it in real life, maybe you want a different constant depending on what you're doing, but 2 is the obvious one because the math also works good, right? So you do 1 plus 1/2 plus 1/4, da da da, and the limit is 2, life is good, right? So it just took you twice as much. Does that make sense? So amortized inserting takes us order of 1, takes us 2 on average-ish. Amortized, it takes us 2 operations. Does that make sense? Takes me 1 copy, which is what corresponds to me. I don't know which one. Maybe this one has 0 copies, but the next one has 1. plus my actual copy to get me to the other. Does that again make sense? So in a vector, how long does it take to insert? Amortized constant. What's my worst case?
You need to make the array bigger.
Which means it is linear, right? Horrible, linear, right? But it's amortized, usually. It's gonna happen when your boss is looking, but does that idea make sense? How about accessing an element in the array? Constant, right? Isn't that cool? How about inserting in the middle? And same as with the linked list, right? But now it's because I need to move this stuff around. How is locality of reference for a vector? Locality of reference.
Should be the same as an array.
Yes, it's fairly nice because it's really an array, right? And so, other than the tiny, tiny elephant in the room, which is that some operations are going to take forever, vectors are amazing. Does that make sense? So we have kind of switched from using linked lists to using vectors.
So would you say in terms of using fairly large ends when you're not focusing on inserting at the beginning as a main focus, the vectors are overall going to be the better data
Yes.
structure? Okay.
Yes. Kind of like, yeah, don't even think about it, use vectors, unless you know what you're doing.
Okay.
And you have tested times and know that vectors suck for your use case, and then you use linked lists. And it's mainly, well, it's first of all the random access for random elements, and then also the locality of reference makes vectors, especially in something like C++, maybe not as much in Java, but in something like C++, makes them obscenely faster than linked lists. It's just a constant, it's just that it's 10 times faster, right? I mean, it's a constant, but the constant's 10 or 20 or something like that. So, yeah. Have you implemented vectors recently? No? Should we go implement them, or should we go implement something like a stack on top of a vector or something like that? Sorry? Stack? Okay. What's a stack? I have it here. What does a stack have? And we're actually going to make it stack of something, right? What are the standard operations for a stack?
Push and pop.
Push, right? It returns nothing, push, and takes an element. Pop, which, well, let's do it. Void, pop, void. I don't do void in Java. And then, I'm not going to do interfaces, I'm just going to do them like this. And then T top. Peak? Sure. Why not? Does this make sense? How do we want to implement it? With a linked list, with the manual vector linked list?
If we do manual vector, we'll learn two things.
Manual vector?
I say linked list because
Link-
the whole point, the whole big thing of a linked list is accessing the
Yeah.
first element.
Yeah. That makes sense. Yeah, for a stack, a linked list is super nice. So let me just actually steal this thing. Right? My constructor actually initializes this to null. Life is good. How do I push an element into the list? Into the stack, sorry. Let me call it top. So top equals new node. No, I cannot do this. Let me do this. Haha. Let me cheat. Let's see if I can figure out all this dot data equals data. I can pass it with t, and what's the next for this element?
The current.
So, not t is element. Does this make sense? Pop. What I want to do is top equals top dot next. Can I always do this? What could happen? There's nothing there. So I don't know whether we should trace an exception or not. What do we want to do? Let's do if top different than null. And for those of you who are surprised and noticed, I have really cool fonts that do horrible things. Isn't that cool?
You're talking about the not equals, I've never seen that before.
It's a font that I have that has ligatures.
Okay.
So it says, oh, bang equal, oh, that should look like that.
Okay. Wow.
Isn't it cool?
All the new toys.
Yeah. What does pick do? Returns the element, so what do I return?
Top.
Top.data, right? And what happens if there's nothing there? Well, I should raise an exception. Oh, I'll be raising an exception. It's probably not the right one, but I'm raising an exception. It's null pointer assignment or something like that, but or null access or something like that. Does this make sense? So what does that enable me to do? Actually, I should. Let's do this. It's empty, right? Or has elements or something like that, right? Let me do it. It's empty. So that enables me to do not st that is empty. What should this print if we didn't screw up anywhere?
It should print the entire stack.
Which is what?
1, 2, 3.
3, 2, 1.
3, 2, 1. Yes.
Because it goes reverse order, right?
Yes.
So in the very unlikely event that we didn't screw up anything, it should print 3, 2, 1. Sometimes it's about as likely as a total eclipse.
Wait, do we
No,
make
I
it?
was just hacked, so.
Do we make it as empty function?
Sorry?
Do we make it as
Yeah.
empty function?
Yes.
Oh,
Yeah,
okay.
sorry. If you guys remind me, I'll put this into a Git repo. It's somewhere in a Git repo. I'll just figure out which Git repo it's on, and I'll send you the link. Does this make sense? I figured out the horrible thing that I have it here for the vector. Oh no, never mind. We could try to implement a vector, but without templates, because it's horrible with templates. Creating a generic array in Java is horrible, because Java uses type erasure for generics, so it loses the type information and doesn't like it when you try to create a generic array. Somewhere in some other repo I have the way where I did it, but not this one, and this thing is empty. So this is a stack with a linked list, right? Super simple. Let's create like an int vector. How about that? Oh, this ends at 6:15.
Yes, sir.
Oh no, let's not do that. You can do that on your own. You did it in data structures. Let's keep talking about the other stuff. So we have stacks, queues. Did you ever do a circular queue?
We talked about it, I don't know if we did it.
Yeah, that's one of those that is nifty, right? The idea with a queue, you're putting on one side and getting out on the other side. You could just grow, right, whenever you need to put, if you have something like a vector, right? If you're doing it with a linked list, what do you do? Well, I just keep a pointer to the last element, right? And life is good, right? Skip a pointer to the last element and insert there, and get stuff out from the front, just like if it was a stack, right? Or the other way around, right? And, life will be good. If I'm doing it with something like an array or a vector, right? What happens? Well, I want to take them out from the beginning, but that leaves me holes at the beginning, right? So the standard trick is to get a bigger array than you think you would need, right? And then wrap around. So once you get, you selected 20 elements, once you get to 20, you go back to 0 and keep going. If eventually you have 20 elements in your list, then you need to grow your array if you are doing a queue like this. In something like a keyboard buffer, what do? You override the poor sucker, right? And that's, if you type super fast, it doesn't happen anymore on keyboards, right? But you could have drop packets in your switch and things like that, because they don't allocate dynamic memory. They just have a queue of this many packets and that's it. Does that make sense? Now, we have heaps, and heaps are actually really, really cool. They are somewhere in between a tree and an array. Trees are the other thing, right? What is a tree? Let's go create a tree node, right? Well, first of all, what kinds of trees do we have? What's the difference between a tree and a list?
The tree has, each node has 2 or more pointers.
Exactly, right? Has potentially at least more than one pointer, right? How many? What's the maximum number? What's the trees that you normally use?
Binary.
Binary, right? In binary trees, what's the maximum number?
Two.
What's the minimum number? Zero, right? You could point to null in both sides. Does that make sense? So my binary tree has 2 pointers, right? Why 2?
That's binary.
Binary is so it's simple, and again, logarithms don't matter, right? If I do a binary tree and I balance it and it's all beautiful, and I have, right? Then my searches, for example, would be log base 2. If I had a ternary, right? Or if I had a base 4 tree with 4 nodes, right? I would have log base 4 instead of log base 2. Is that much better? It's a constant factor. Who the hell cares? Your boss. But does that idea make sense? So we normally use binary trees. That's actually not true. In databases, we tend to use multi-way trees because we want to pack stuff onto pages on disk that have a specific size. And in fact, a lot of the balancing things came up in from databases. You probably saw a binary search tree, right? It's a binary tree with one other thing. What? Elements to the left are lower and elements to the high are bigger, right? What do I implement with binary search trees? Allows me to implement sets fairly quickly because I can check whether an element is there, and allows me to implement maps, right? That attach a value to a key, right? Dictionaries if you do C# rather than Java, maps in Java and C.
Could you explain that a little bit more exactly how it can be used to implement a map?
Okay. I'm not gonna explain anything, I'm gonna build stuff.
Okay.
Maybe I was building this stuff, yeah, but it's horrible. There it is. We have this, right? If I'm implementing a set, this is what I have. If I'm implementing a map, I have this, right? I keep a key and a value and pointers to the left and right, right? And BST is for binary search tree node. So how can I implement this? Let me create a binary search tree. We have 5 minutes. More than enough time. Let me do horrible things because we have 5 minutes. How do I search? So v get k key. Right? How do I search? If my search ought to be recursive, of course. So I'm gonna have a static, or put it on the node or something like that.
So it's pretty much the same as a binary search tree, but you have an extra value that you call
Yes.
value that you can't use to search. Like you can only use the key to search for it.
Exactly, and then you
Okay.
return the value.
Okay.
Yes,
I
it is.
thought, yeah, that's all.
That is exactly what. That's exactly what it is. Yes. greater than. Um, is basically
Yeah.
this. And nothing compiles. As it should be. We'll fix it next class. How fast is searching on a binary search tree?
Logarithmic.
Always?
Worst case log.
Best case log n, or usually log n. What does the binary search tree also has to have to be log n?
Balance.
Balance, right? If the tree is unbalanced, what's my worst case? N, right? If the tree is balanced, then I get log n. And so there is 700 different algorithms for balancing, right? What balancing does is usually it makes my insertions and things like that also take log n time, and I may need to do log n balancing things. But balanced trees search allows me for searches, insertions, and deletions in log n time. There is 3 or 4 well-known different algorithms. So next class we'll start from there and we'll go into hash tables. And then we'll probably super quickly do sorting and be done with it forever. You will know all this stuff. Let me come here and stop this.